Hello, welcome to the second of the Quest tutorial videos. In this video I'll be talking about a lot of the theory behind how Quest works. So I'm just opening the help file that comes with Quest, and I'll just briefly talk about the tensor quantities that you can set in Quest. So the first one is for the quadrupolar or EFG tensor. You have the quadrupolar coupling constant, which is defined as such, and the asymmetry parameter, which defines the asymmetry of the EFG tensor. So this value takes a value of 0 if you have an actually symmetric EFG tensor, so v11 is equal to v22, and it has a maximum value of 1 for a perfectly asymmetric EFG tensor. This is where there's a lot of different conventions out there for the chemical shift tensor. So in Quest, we use the same convention as is used in W solids, where the eigenvalues of the chemical shift tensor are ordered as follows, with delta 11 being larger or equal to delta 22, larger or equal to delta 33. And the Maryland convention is used for defining the chemical shift tensor in Quest. So you have the isotropic chemical shift, which is just the average of the three components, the span, which is the breadth of the chemical shift powder pattern, and the skew, which takes values from -1 to 1 to just express the asymmetry of the chemical shift tensor. So these are ordered by not by magnitude, but by the actual values of the chemical shift tensor components. So this is different than what is done in, for example, DM-Fit and Simpson, but it's consistent with what is in W solids. The Euler angles in Quest are from a passive ZYZ convention, so it's the same one as is used in W solids, but it's different as what is in DM-Fit and Simpson. So if you're more used to using Simpson or DM-Fit, then I suggest that you look up the program Trafo, written by Dr. Klaus Eichele. And this program should let you make these transformations of Euler angles from one reference frame to another. And so in our Euler angle convention, for example, it's the magnetic field which is rotated away from the chemical shift tensor in 3 subsequent rotations about z, y, and then z, such to reorient the chemical shift tensor relative to the EFG tensor. So just keep that in mind whenever you're simulating your NMR spectra, that there's these different conventions out there. So this one is the same convention as in W solids, but it differs from that of other programs. To make the actual NMR calculations, what we do is we calculate the frequency at a bunch of different crystallite orientations. And to do this exactly, we have to express the quadrupolar Hamiltonian, which is just given here. And these different components can be expressed using these Cartesian tensor magnitudes, which can then again be expressed with a set of 2 angles, theta and phi, which represent the orientation of the EFG tensor in the magnetic field. So to do the actual NMR calculation, you have to do the sum of both the Zeeman and the quadrupolar Hamiltonian. So for the matrix elements of the Zeeman, the combined Zeeman quadrupolar Hamiltonian are as such, where the diagonal elements actually have this this component which comes from the Zeeman interaction, where the chemical shift is added in there. And the problem there, again, why you need to use perturbation theory or exact theory to simulate quadrupolar NMR spectra, is because that you have these off-diagonal terms. And so these Zeeman wave functions aren't actually true wave functions of the Zeeman quadrupolar Hamiltonian, because that you have these off-diagonal elements. The way that you force this to be the case to get the true wave functions out is you just diagonalize this matrix out. And what this gives you is it gives you a set of eigenvalues from the diagonalization, and these eigenvalues are simply the energy levels, and you can use these to calculate the resonance frequencies. And from the eigenvectors, which represent the new wave functions, which are expressed in the basis set of these Zeeman wave functions, you can use these to basically calculate the line intensities. So in Quest, for example, the line intensity is calculated with the use of the Sx operator. So this corresponds to a coil perpendicular to the magnetic field. Although I've added an option to change the coil orientation for a spin 1, because this might be useful for overtone NMR spectroscopy that I'll discuss in a later video. So the calculation is done for a various number of orientations to simulate a full powder, and the way that we do this to have a good speed in the calculations is we use the powder algorithm of Alderman, Grant, and Solom. And what we do in this case is we actually, instead of averaging over a full sphere, we average over an octahedron, or half an octahedron, and we only need to calculate the frequency at the edges of all these triangles here, at all the little corners, and then we can do a linear interpolation to fill in the rest of space between these corners. So this brings me back again to the actual program. So in Quest, the value which is given here for powder average quality actually corresponds to the number of triangle faces along this edge. So for example, this image here corresponds to a value of powder average quality of 6, because there are 6 triangle edges on the edge of this octahedron. And so you can systematically increase the quality of the powder average, which will increase the number of orientations that you need to calculate, so the time goes up, but you should get a smoother line shape as you do so. So for example, if we put a powder average quality of 1, then this only calculates 3 orientations, and this is the spectrum that you get. So the 3 frequencies are actually those of the 3 corners of this triangle. And you can increase this powder average quality, and as you increase the number of orientations, you can see that it starts taking a familiar quadrupolar line shape. And as you increase it to a large enough number, you should get a smooth enough line shape. So by changing this powder average quality, you can again trade off speed for quality, for example. So when you're fitting your spectra, if you want a faster fitting, you can reduce this number to a smaller value, because that the singularities remain at the same positions. So I hope that this helped clear up a few things about how Quest works, and I'll be talking to you in a later video.